Hi everyone. This video is a brief introduction to activity, which is probably a topic that you haven't heard of before, and it's very important for chemical equilibrium. So let me ask you to recall that if we had the dissociation of silver chloride into silver ions and chloride ions, you were taught to write the Ksp as the concentration of silver times the concentration of chloride. But it turns out that this expression is true only under certain conditions. What we really should use when we write our KSP expressions or any expression for equilibrium is not concentrations but rather activities. So KSP should be the activity of silver times the activity of chloride. So this capital A represents activity, and we'll have an equation for activity, but for right now, let's just say that it's similar to concentration. It's similar to concentration. It must be if we're able to plug it in for concentration into our KSP, but it accounts for solution composition or the presence of spectator ions. And we'll have a way to quantify the presence of these spectator ions using a quantity called ionic strength. And we'll talk about ionic strength a little bit later. For right now, I want to show you how the presence of spectator ions can affect the solubility of salts. If you look here, we see the solubility of silver chloride given at different KNO3 concentrations. And what we see as we increase the KNO3 concentration is that the solubility of silver chloride increases, doesn't it? So the solubility increases as spectator ions increase. Now, just to be very clear, when I imagine this experiment, I imagine a beaker of water and some silver chloride here, and I imagine increasing concentrations of potassium and nitrate, right? So if I think about the dissociation of silver chloride, why should KNO3 have any effect on shifting this equilibrium to the right? Because that's what happens when you increase the solubility, doesn't it? You're getting more ions in solution, and I'm wondering why that happens. It's not like we have a common ion or anything. So in order to understand that, we're going to have to consider this silver ion in two different environments. Let's imagine that we have a silver ion dissolved simply in water, and then our other environment will be a solution of KNO3. And how might this silver ion look dissolved in water? Well, when silver is dissolved in water, obviously it'll be surrounded by water molecules. And noticing that I'm orienting the oxygen atom, which has a partial negative charge, towards the silver ion, which has a positive charge. So in water, we can think of the silver ion as having a so-called hydrated radius. It's surrounded by water. But how does the silver ion look in a solution of KNO3? In a solution of KNO3, this silver ion will be surrounded by a little bit of water, but won't it also be surrounded by these negatively charged nitrate ions? Don't opposites attract? And wouldn't those negatively charged nitrates surround that silver ion such that in a solution of KNO3, we no longer have simply a hydrated radius. Instead, we have a so-called ionic atmosphere. And that ionic atmosphere tends to hide the silver ion from the chloride ion. So in a solution of KNO3, you have your silver, which has a negatively charged ionic atmosphere. These are all of those nitrates surrounded by that silver. And then chloride, wouldn't it be surrounded by potassium ions in KNO3? So chloride's ionic atmosphere would have a positive charge. And these ionic atmospheres prevent the silver and the chloride from coming together. So again, these ionic atmospheres that you get in KNO3 prevent the silver chloride precipitate from forming. And that's why the solubility of silver chloride increased in the presence of KNO3. Let me show that to you again. Again, that solubility increased in the presence of KNO3. So in the next video, we're going to learn about ionic strength and how we quantify the presence of these so-called spectators. Hope you enjoyed the video and thanks for listening.